Now we're going to look a little bit at fatty acids, and the reason we look at them here is because they actually incorporate a couple of different functional groups. Now, when we look at a fatty acid, what we see is kind of the same in every molecule. There's some variations in the number and the types of bonds we see, but we always see the same basic structure. And what we see first is this long chain of alkane chain. Occasionally there's an alkene in there, but a long chain of carbons. And we see this carboxylic acid functional group here at the end. And this is the polar end of the molecule. And then we have our non-polar end of the molecule. So you can see that as we get to bigger and bigger molecules, the non-polar portion becomes a much bigger factor than the polar portion. So when we look at things that are fats, we're looking at usually very long carbon chains, and as a result, they don't mix with water. So if you look at fat and water, you're going to see the fat rise to the top. It's not going to stay dissolved in the water. Well, we'd never see advertisements like this, but this is actually what lard is. It's stearic acid. Now, your grandmother, probably not your grandmother, probably your great-grandmother, probably used lard when they were cooking, and this is a fat that comes from animals, and it is a saturated fat. Now, saturated fat is something we hear in the news a lot, but all it means is that there are no double bonds. We talked about saturated hydrocarbons. They had the maximum number of hydrogens, all single bonds. Saturated fats are no different. It just means there's all single bonds. Now, there's some nutritional consequences to saturated versus unsaturated, but chemically, it means the same thing as when we're dealing with a regular saturated hydrocarbon. So in this table, we actually see a whole list of saturated fatty acids. You do not need to memorize them. It's just given here as some examples. One thing to notice is that there tend to be even numbers of carbon atoms, and we'll get into how fats break down in our body later on in the course, and we'll see why that that pairing of carbon atoms is important. But for right now, just know that there are even numbers. I don't expect you to memorize, for example, that stearic acid is 18 carbons and palmitic is 16. What I do want you to know how to do is, if I say draw a fatty acid that has 12 carbons, that you can draw it because you know there are 12 carbons in total, and you know it has this carboxylic acid group on the end of the molecule. Now, here they've shown the condensed structure and the skeletal structure where they're showing the double bond O and OH. There's kind of an alternative ending to showing the condensed structure. If I'm just looking at this last COOH, I could also write that as COOH. And we mentioned that when we were talking about the functional groups, just as a shorter way of showing it, because it's not always easy to draw in the double bonded oxygen up on top. But what we have here at the end is exactly the same as what we've drawn here. When we look at unsaturated fatty acids, all that means is now we have at least one multiple bond. We typically see double bonds when we look at unsaturated fatty acids. Rarely, if ever, do we see triple bonds. Sometimes we see a single double bond. Sometimes we see multiple double bonds. In this example, we're looking at a single double bond, oleic acid. We still have the same basic layout of our molecule. We have the long non-polar part of the molecule. We have a double bond there in the middle. And we still have our COOH group, our carboxylic acid group, here in the structure. None of that's changed. With the introduction of that double bond, it does something interesting to the actual geometry of the molecule, or the shape of the molecule, in that we kind of see this big U shape. We see this bend happening in the molecule. And because of that bend, it's going to interfere with how this molecule is interacting with other molecules around it. And that changes some of the properties because of that double bond, and therefore, and because of that bend that exists. So what's the big deal when we talk about saturated versus unsaturated fats in our diet? Well, when we look at saturated fats, we know we have all single bonds because all of our carbons have the maximum number of hydrogen atoms. And because that, we have these linear molecules. We do have a zigzag in them, but they're fairly overall as basically a line forming. And what we see happening is when I have lots of those linear molecules, they can stack up nice and neat. So if I have a pile of Pringles, I can stack them all up very nice and neat. And what I see is there are lots of points of contact between the Pringle on top and the second one and the third one and so on. And so there's lots of interaction kind of locking them in together. When I look at unsaturated fats, which are healthier fats, what I see is I've got this bend in that molecule. And because of that bend, now these molecules are not stacking up so nice and neatly. Now they look more like potato chips, where I see that I can kind of make a pile of them, but I don't get as much contact between each individual chip as I did with the Pringles. Now imagine this in your body. If I have lots of saturated fat in your body, say in your bloodstream and going through your arteries, I've got lots of points of contact with this molecule and the walls of your artery. And this is where we can get some artery buildup of fats in our body. It doesn't happen quite so easily with our unsaturated fatty acids because of that shape. What we see is that we can actually not have as much interaction between the walls of our artery and the molecule. We also see it, we get to a change in the melting points of these two substances. Because these molecules are stacked so nice and neatly, and because they can interact with each other along the full length of the molecule, it's going to take more energy to break them apart. So we get a higher melting point than we do for an oleic acid, which has a one double bond in it. So it's not as nice and neat and organized, and as a result, it's easier to pull these molecules, the oleic acid molecules, apart from one another. So this is why our unsaturated fats tend to be in the liquid phase, and our saturated fats tend to be in the solid phase. So this is another table. These are unsaturated fatty acids. We see some names and structures. Again, you do not need to memorize these either. What I want you to recognize is, one, that something is either monounsaturated because it has a single double bond, or it is polyunsaturated because it has multiple double bonds. What we see is that as we increase the number of double bonds, we also decrease the melting point for these substances. And so when I look at something like olive oil and corn oil, they're going to have a higher melting point than, say, soybean oil or canola oil. Another thing to notice is when we look at this table, we also see this carbon designation as omega-3, omega-6. And we hear a lot about omega-3 fatty acids in nutrition, that they're very good for us and our body needs them, and our body does need them. And there's a lot of debate about whether the omega-3 fatty acid supplements do any good or it's just a waste of time. That's a whole other topic for discussion. But what they're talking about is when they're looking at this omega-3 and omega-6, and you don't have to worry about what it actually means as far as which carbon, but all it's telling is, where do we see the first double bond? That's all we're looking at here when we see this omega-6 and omega-3. So here we see it on the third carbon, here we see it on the sixth carbon, here we see it on the seventh carbon. That's all the omega means. Okay, I'm not worried about you knowing that, but I just like to bring that in here because you hear about it in nutrition circles and hear about it in the news, and they talk about omega-3, so you know exactly what it means. So now an omega-3 unsaturated fatty acid just means that there's at least one double bond in it. The first double bond happens on the third carbon, and then there has to be at least one double bond because it's unsaturated. So don't need to memorize this. You don't need to memorize the other table with the saturated fatty acids either, just knowing the general characteristics of their structures. Long carbon chain, carboxylic acid group. Saturated is going to be all single bonds, unsaturated, one or more double bonds. That's the critical thing we're worried about here. If you have questions on this, please let me know. They bring in fatty acids here. We'll pick these up again when we look at glycolysis, and we look about breaking down glucose and how our body breaks down fatty acids to get energy out of them and use them to produce ATP in the body. So that's it for this section on the functional groups. If you have questions, let me know. Again, don't be freaked out about the memorization. You don't need to do that. Just worry about understanding the basic characteristics of a fatty acid and understanding how the skeletal structures and the condensed structures of those molecules relate to one another.